Hi everyone, in this talk, I will present our paper called Disentangling Masked Autoencoder for Unsupervised Domain Generalization. We all know that distribution shifts are well spread. For example, the model could only access 4 syn domains during the training process. However, model could encounter countless data from unseen domains. This gives rise to a problem called domain generalization, where the model only trained in limited domain and tested in unlimited unseen domains. And the key point in domain generalization is how to utilize class label more properly. However, we notice that unsupervised data is never sufficient for a large foundation model, and also the performance depends on the inductive bias derived from the available labels. This makes us wonder, what if we don't have those class labels and only have domain labels? The context of insufficient class labels gives rise to a new research topic called unsupervised domain generalization, and this is a much challenging task than the original DG. But how could we deal with UDG? We could observe that the performance fluctuates in different domains and has a huge misclassification in unseen domains. This urges us to capture domain invariant features. We call it the domain invariance principle. And also, we could observe obvious entanglement between invariant feature and domain-specific feature. We try to illustrate through a T-sim visualization. We visualize the embeddings of the MAE. Each point represents an input image and is color-coded with the domains. We observe that some area display the domain invariance. We could easily tell each domain has its unique distribution and have its domain-specific part. This problem urges us to decouple domain invariant and the domain-specific feature. We call it the disentanglement principle. But implementing these two principles can be easy. Images always show strong heterogeneity. For example, we show 2 pairs of images. We could tell that the similarity between the domain pairs is much bigger than the similarity between the class pairs. We have to admit that sometimes the variation similarity is bigger than the class similarity. Note that we don't have the class label to remind the model what is the semantics and what is the variations. We only have the domain labels in UDG, so how could we implement these 2 principles? We devise a framework, use 2 autoencoder, a decoder, and a domain classifier. We hope 2 encoder can help disentanglement and a domain classifier can help domain invariance. We have 2 loss functions. Apart from the conventional reconstruction loss term, we devise an adaptive contrastive loss. We use SI to donate the semantics of feature of image XI, and VI to donate the variational feature of image XI. And we then keep the semantics as the same, and we concatenate a variation Vj from intradomain images Xj to generate negative samples to disentangle semantics and variation further. By using hard negative samples, we can further disentangle semantics and variations. And also, we draw inspiration from the inverse propensity weighting in causal inference. We inversely multiply probability to reweight the loss. We show this in this expression. Probability P here is the predicted score for the ground truth domain. This adaptive contrastive loss compare our model to refine domain invariant semantic encoder learning. This also helps us to achieve the domain invariance principle. Then we show the experiment. Firstly, we show the reconstruction image to validate our disentanglement principle. We mainly visualize the results in 2 datasets, non-biased, columnist, and domain net. We concatenate the same semantics with different variations to generate reconstructed images. We can tell that the semantics and variation are perfectly disentangled in the feature space. After that, we try to prove the domain invariance through the feature embedding level. Similar to previous image describing MAE, each point represents a real image. The color is coded with the domains. If we look at the embeddings, we can find that the feature captured by the semantic branch uniformly scattered in the feature space, and images with similar semantics are more likely to cluster closely, regardless of the different domains. And if we look at the embeddings of the variation branch, we can find that each domain displays a unique distribution, and images with similar variations are likely to cluster. These 2 visualizations further validate our domain invariance principle. Then we show our empirical results in UDG. We mainly conduct our experiments on the domain net. The empirical results show that our model could constantly achieve improvement over the competitive baselines. And that's it. Thanks for watching.